The final chapter of this course is about phase transitions. And I would like to start with a little reminder of the issue of stability and instability. We had found, that was Le Chatelier's principle, that in order for a system to be thermodynamically stable, the specific heat at constant volume and the isothermal compressibility must be both positive and finite. Or more precisely, that's how we originally obtained that, we must have that the inverse of specific heat and the inverse of isothermal compressibility, that these must be strictly positive. And what we're going to see is that this condition may be violated, not necessarily, not always, but in many cases, this stability condition or these stability conditions may be violated at a phase transition. More generally, you can often recognize phase transitions by the fact that some thermodynamic coefficients, doesn't have to be these two, but can be others, some thermodynamic coefficients may diverge or show some other kind of discontinuity. And what this means, well, if you have, say, a diverging specific heat at a phase transition, this would mean that the stability condition is no longer satisfied, and therefore a formerly homogeneous phase may now spontaneously separate into two different phases, which of course then are no longer homogeneous. They may be homogeneous within themselves, but the total system is no longer homogeneous because you have a spontaneous split into two different phases. The appropriate thermodynamic potential to describe a phase transition is usually the free enthalpy. This is true whenever a phase transition occurs in open air. So when you see water, liquid water evaporating in open air, then the system is coupled to the atmosphere as a reservoir that maintains both a constant temperature and a constant pressure. So whenever you have a phase transition occurring at a given temperature and pressure, so you have the system coupled to a reservoir that maintains constant temperature and pressure, then you should use the free enthalpy. So we are considering here the situation where the system splits at the phase transition into two phases. We may have a liquid phase and we may have, say, a gas phase, or this can be characterized in a different way. We have, in any case, we have a phase 1 and phase 2. They coexist at the phase transition under the influence of, or coupled to, a reservoir maintaining temperature and pressure. So this is the first observation, that when we have fixed temperature and pressure, then we should use the free enthalpy G, which has temperature, pressure, and also particle number as its natural variables. Here I start to write particle number explicitly, because particle number will no longer be a constant. We have a transformation between the two phases, so particles will move from one phase to the other, and therefore we can no longer consider, for an individual phase, we can no longer consider the particle number to be constant. And that's why I start to write this dependency explicitly. Now, each phase has its own free enthalpy. So we have phase I, which may be 1 or 2, but in general you can also have more than 2 phases coexisting. So we have phase I, and this has its own free enthalpy, Gi. They all depend on the same temperature and pressure because they are maintained by the reservoir. All phases are coupled to the same reservoir, so we have the same temperature and pressure. But the number of particles in phase I may vary by phase. So in phase I we have Ni particles. Now the whole system is no longer homogeneous, but each phase in itself is. So if I have coexistence, say, of liquid and vapor in a container, then obviously the content of the container is no longer homogeneous because I have these 2 distinct phases. But the liquid in itself is homogeneous, and the vapor, the gas in itself, is also homogeneous. This implies that the thermodynamic potentials are extensive quantities. You remember that one important conclusion of homogeneity is that you have this clear distinction between intensive and extensive variables, and the thermodynamic potentials are all extensive variables. So in particular, the various free enthalpies of the various phases are extensive. At the same time, we know that the partial derivative of the free enthalpy of phase I with respect to the particle number in phase I at fixed temperature and pressure, that this equals the chemical potential of phase I. The chemical potential may vary across the various phases, so each phase has its own chemical potential. I don't know if this is obvious to you, that the partial of free enthalpy with respect to particle number is the chemical potential. That's why I prepared an extra page to just briefly show you this relationship, and then we come back to the previous page. Now, remember, good physicists have studied under very fine teachers. We know that the free enthalpy equals internal energy U minus Ts plus PV. This means that the differential of free enthalpy, this is du minus S dt minus T ds plus V dP plus P dV. Now, when we allow for variation of particle number, then the differential of internal energy is given by TdS minus PdV plus mu dN, chemical potential, times differential of particle number. This is du when we allow for changes of particle number. And then we have the remaining terms. So minus S dt minus TdS plus VdP plus PdV. And now, several of these cancel. TdS cancels, PdV cancels, and we find that dG is minus S dt plus VdP plus mu dN. And from this form of the differential, you recognize that the chemical potential mu must be the partial derivative of free enthalpy with respect to particle number at fixed temperature and pressure. This is the relation that I had used on the previous page. So let's go back. The fact that the free enthalpy is extensive and it depends on, it has as its natural variables two intensive variables, T and P, and one extensive variable, namely the particle number. This implies that the free enthalpy must in fact be proportional to particle number. If I increase the size of the system by a factor x, so I multiply all extensive quantities by a factor x, so I replace particle number n by x times n, then I must have x times the free enthalpy, because it's extensive. And this implies that the dependency of free enthalpy on particle number must be linear. So Gi, as a function of temperature, pressure, and particle number, this must be proportional to particle number. Now the factor of proportionality, this must be the partial derivative of free enthalpy with respect to particle number. But this, we just learned, is the chemical potential. So the factor here is, in fact, the chemical potential, and we simply have free enthalpy equals chemical potential times particle number. Now, by the Gibbs-Duhem relation, which also holds for homogeneous systems, by the Gibbs-Duhem relation, the three intensive variables are not independent. So when you have three intensive variables, then only two of them are independent. And it's always possible to express one of the three as a function of the other two. That was Gibbs-Duhem. Now here we have three intensive variables in this line. We have the chemical potential, we have the temperature and the pressure, and the Gibbs-Duhem relation tells us that the chemical potential must be a function of temperature and pressure. So we can write mu as a function of temperature and pressure. This is by Gibbs-Duhem. So this is was our third observation, that for each individual phase, the free enthalpy can simply be written as chemical potential of that phase, which depends only on temperature and pressure, times the number of particles in that phase. The next observation is that all the phases are coupled to the same reservoir. And we had learned that when two subsystems are coupled to the same reservoir, then the appropriate thermodynamic potential is additive. And the total free enthalpy of the combined system, including all the phases that are coexisting, that is a function of temperature and pressure, which are maintained by the reservoir. And it's a function of all the particle numbers of all the phases. And it's given simply by the sum of the free enthalpies of the various phases. And each individual phase has the free enthalpy chemical potential as a function of temperature and pressure times particle number in that phase. So in the case that we have two phases, that would be mu1 times n1 plus mu2 times n2. And once again, I would like to stress that for two different phases, these are two different functions. So phase 1 may have the function mu1 of T and P, and phase 2 has a different function mu2 as a function of T and P. Next observation. While the number of particles in the various phases may vary, when you have a transformation from one form in the phase into the other, then the number of particles in phase 1 may decrease, while the number of particles in phase 2 may increase. But the total number of particles is, of course, constant. And therefore, when we have two phases, then this means that N1 plus N2, which we call simply N, total particle number, this is of course a constant. So we can rewrite the total free enthalpy of the combined system for two phases. We can also write that as N1 times mu1 minus mu2 plus the total particle number n times mu2. So when for n you insert n1 plus n2, then you see that this will reduce to the form that we had on the previous page. So it's an alternative way of writing the total free enthalpy. In equilibrium, the total free enthalpy of the system must attain a minimum. So, still in the presence of our reservoir, equilibrium is characterized by a minimum of the total free enthalpy. Let's plot the total free enthalpy as a function of the number of particles in phase 1. The number of particles in phase 1 can be anywhere between 0 and the total number of particles n. Let us distinguish three cases. Let us consider the case where the chemical potential of phase 1 is larger than the chemical potential of phase 2. Let's consider the case where the chemical potential of phase 1 is smaller than the chemical potential of phase 2. And finally, the case where the two chemical potentials are equal. In all three cases, when the number of particles in phase 1 is equal to 0, then look at the formula above. N1 is equal to 0, and then the total free enthalpy equals the total number of particles times mu2, times the chemical potential of phase 2. So in all cases, when N1 is 0, the total free enthalpy equals the total number of particles times mu2. If the chemical potential of phase 1 is larger than the chemical potential of phase 2, then again looking at the formula above for the total free enthalpy, mu1 minus mu2 inside the bracket is positive. And therefore, as you increase N1, you add to the initial total free enthalpy, you add something positive. So the total free enthalpy increases as you increase N1. You have a straight line going upwards with a positive slope. If, on the other hand, the chemical potential of phase 1 is smaller than that of phase 2, then mu1 minus mu2 is negative, and as you increase N1, the total free enthalpy decreases, and you have a negative slope. If, on the other hand, the two chemical potentials are equal, the bracket is 0, and the total free enthalpy is independent of N1. It always maintains the same value, N times mu2. So then you have a horizontal line. Now what about equilibrium? So equilibrium is always characterized by a minimum of total free enthalpy. In the first case, where mu1 is larger than mu2, you have the lowest total free enthalpy when N1 is equal to 0. Equilibrium is here. So in this first case where mu1 is larger than mu2, equilibrium is at N1 equal to 0, and this means that all particles are in phase 2. You have only phase 2. In the case where the chemical potential mu1 is smaller than mu2, you have the lowest total free enthalpy when N1 is equal to N. So equilibrium is here. In equilibrium, you have only phase 1 because N1 is equal to N, total particle number, so all the particles are in phase 1. And in the intermediate case, so where the two chemical potentials are equal, there is no unique minimum of the total free enthalpy. So in the case where the two chemical potentials are equal, equilibrium can be anywhere along this line. So N1 can vary between 0 and the total particle number. So in this intermediate case, both phases can coexist at arbitrary ratios. What we learn from this simple consideration is that in order for two phases to coexist, they must have the same chemical potential. So we derive from this the coexistence condition that the chemical potentials of the two phases must be equal. I should add that this figure that I drew is, of course, at constant temperature and pressure. And they are maintained by the reservoir, and all we vary is the number of particles in phase 1. Let me now draw another picture. Let's now keep only the temperature fixed. So the temperature is fixed, but we vary the pressure, and we look at the behavior of the chemical potential as a function of pressure at fixed temperature. Now the two phases have different functions, mu as a function of temperature and pressure. Phase 1 has, say, this function here, mu1 as a function of temperature and pressure. Temperature is held fixed, so only the pressure is varied, and this is some dependence of mu1 on the pressure at fixed temperature. Phase 2 has a different chemical potential, mu2, as a function of temperature and pressure. So when the temperature is held fixed, then it generally varies with pressure in a different way. So we have two curves representing the chemical potentials of the two phases as a function of pressure. If there is a point where these two functions, these two curves intersect, then we learned that at this point we can have coexistence of phases. So at this point, the two phases can coexist. And this happens at a certain pressure, P star, which generally depends on the temperature that we are keeping fixed. To the left of this point, so at a lower pressure, in this example, the chemical potential mu1 is larger than the chemical potential mu2. And we had learned that when mu1 is larger than mu2, then we have only phase 2. That's from the figure above. So to the left, at a lower pressure, to the left of this coexistence point, we have only phase 2. And to the right of this coexistence point, mu1 is smaller than mu2, and we had learned that when this is the case, we have only phase 1. So we have, to the right, we have phase 1. Let me draw one last figure. Let me now draw a diagram that shows pressure and temperature. Let me indicate in the left diagram a pressure below this critical pressure P star, where the phase transition occurs, and another pressure above P star. And let's consider a process where we start from pressure Pi, so the initial pressure Pi, and we increase the pressure at constant temperature up to the final pressure Pf. So in the right diagram, this would correspond to a process where we start at some initial pressure Pi, some low pressure Pi, we increase the pressure at fixed temperature. So we move upwards. We move upwards up to some higher pressure, some final pressure Pf. And somewhere in between, there is this pressure P star. At some fixed temperature T0, then the location of this critical pressure P star generally depends on the chosen T0. So I would like to write more precisely that the P star depends on T0, on T0. We had seen in the left picture that at pressures above P star, we have phase 1. So up here, we have phase 1. Below P star, we have phase 2. And at P star, we have the phase transition. So here is the boundary between phase 1 and phase 2. Now this holds true for arbitrary temperatures that we keep fixed. So now we can start to vary the T0. We can go to the left, and we find a different critical pressure P star at which the phase transition occurs. Let's say it's a bit below the first one, and then we go further to the left with T0, and at every temperature that we keep fixed, we find the corresponding P star where the phase transition occurs. And we can continue that on both sides, and we get a curve. And the curve indicates where in the PT diagram the phase transition occurs. This is the so-called coexistence curve. And it is the curve on which the chemical potentials of the two phases are equal, and therefore the two phases can coexist. So it's the curve on which mu1 of T and P equals mu2 of T and P. And the curve shows the function P star as a function of T. And one final remark, this curve may or may not end. So there might be, but there doesn't necessarily have to be, a point where this curve ends. So this is the last remark here, that this curve may or may not end.